Today we're going to be looking at properties of radicals. So a radical is like a square root or a cube root. Here are your state standards that go with this lesson. Below you'll see your success criteria. So to be successful with this lesson, you need to be able to use properties of square roots to write equivalent expressions. You need to be able to use properties of cube roots to write equivalent expressions. You need to be able to rationalize the denominator of a fraction, and you need to be able to perform operations with radicals. All right, we have several vocab that's very important. Make sure you get these in your notes. What you need to do is just pause the video and copy them in your notes. All right, so a radical expression is an expression that contains a radical. So if it has a square root or a cube root, again, remember that's a radical. Simplest form of a radical, an expression involving a radical with an index n, is in simplest form when these three conditions are met. No radicands have perfect n powers as factors other than 1. No radicands contain fractions. No radicands appear in the denominator of a fraction. So those are three things that you need to remember and take note of. Rationalizing the denominator. When a radicand is in the denominator of a fraction, you can multiply the fraction by an appropriate form of 1 to eliminate the radicand from the denominator. This process is called rationalizing the denominator. So when it says an appropriate form of 1, there are different things that you can do. So if you have like 4 divided by 4, you know that 4 divided by 4 equals 1. That's equivalent to 1. Or if you have the square root of 2 divided by the square root of 2, that's equivalent to 1. Anything divided by itself is equivalent to 1. So when we're rationalizing the denominator, we're going to multiply by a fraction that's appropriate form of 1 to eliminate that. So we'll look at examples of that. Conjugates is probably a new term for you. Make sure you are aware what a conjugate is in math. Two pairs of binomials with identical terms but sharing opposite operations, which means different signs in the middle, like a plus minus. These are considered conjugates. So here's an example. If you've got a square root of b plus c square root of d, here you got the same binomial, but this one has a minus where this is a plus. Together, these two binomials are considered conjugates. And we will see why that's important when we're dealing with radicals. Like radicals, so to have like radicals, it means the radicals with the same index. So if you have a square root and a square root, you can multiply those. If you have a cube root and a cube root, you can multiply those, but not a square root and a cube root. All right, one of your key ideas here, product property of a square root. So if you have a square root of 5 times the square root of, square root of 9 times the square root of 5, you can pull those two apart because 9 is a perfect square. So you're going to write the square root of 9 times the square root of 5. The square root of 9 is just 3, so you have 3 square roots of 5. So this 3 square roots of 5 is equivalent to the square root of 9 times 5. And actually 9 times 5 is 45. So if you started with the square root of 45, you could rewrite it as this. Quotient property of square roots, very similar. If you have the square root of 3 over the square root of 4, you can, that can be all under one square root, the square root of 3 over the square root of 4. Again, the square root of 4 is a perfect square, so if we separate those, we can reduce that to 2. Square root of 3 is not a perfect square, so it's going to stay just in that form. All right, we're looking at example 1. It says using the product property of square roots. All right, so we have the square root of 108. So what you want to do is find the largest perfect square and then rewrite this as a product of two numbers. You can see here, I've got the properties here listed for you, the square root of 9 times 5. So originally that would have been the square root of 45, but they rewrote it as 9 times 5. So let's look at perfect squares. So here is a list of our multiplication table. So 2 times 2 is 4. 4 is a perfect square. 9 is 3 times 3, 16, 25, 36, 49. These numbers are your perfect squares. So you have to find the largest number, the largest perfect square that goes into 108. So let's check our numbers here. All right. All right, my calculator does not want to cooperate here. So we are just going to look at it where it's at. So let's see, 108. So let's see what goes into 108. All right, so we've got 108, 4. We know that 1 goes into everything, but let's see if 4 goes into 108. Well, what did I do? I forgot my 4. All right, let's try one more time. 108 divided by 4. Yes, it goes evenly 27 times, but 27 is also 9 times 3. So I feel like there's a bigger one here. So I'm going to do 108. My next perfect square would be 9. So let's divide it by 9. Again, we're looking for our largest perfect square. So 9 is a perfect square. 12 is not a perfect square, but 4 times 3, again, there's another one in there that we're missing. So let's go 108 divided by, our next perfect square is 16. And again, you need to commit these perfect squares to memory, and then you don't have to have the chart. 108, 16 did not work, so let's try 25. And when I say it didn't work, I mean it didn't come out evenly, so you don't have two nice numbers, two rational numbers, integers that multiply to give you 108. So let's do, after 25 comes 36, so let's do 108 divided by 36. All right, so 36 is 6 times 6, 6 squared, and 3 is a prime number. So I know that 36 times 3, this is going to be my largest perfect square. So even though 4 was a perfect square and it worked, 9 was a perfect square, it worked, those were not the largest perfect squares. So I had to keep going till I found the largest perfect square. So 36 times 3 is 108. So let's do the square root of 36 times the square root of, I think it was 3. 36 times 3 is 108. Yes. All right. So that is the product property. Product means multiplication. And then we can see that the square root of 36 is 6. And then the square root of 3 is not a perfect square, so it stays underneath the radical sign. All right, the square root of 9, we can write that as the square root of 9 times the square root of x squared times the square root of x. So why did I separate the cube of the x cubed into x squared times 1? Because property of exponents says if I have the same base, I add exponents, and I'm looking for everything that's a perfect square that'll come outside the radical sign. So the square root of 9 is 3. The square root of anything squared is just that number. And then the square root of x, this one is not a perfect square, so it stays underneath. All right, using the quotient property, we're going to look at something very similar. We want to see if we can find perfect squares there. The square root of 15 is 3 times 5. Neither is a perfect square, and 15 is not a perfect square. But what about 64? All right, if you need to look at the chart again, is 64 a perfect square? It is. 8 times 8 is 64. Okay, again, you should have this multiplication tables memorized, but if you don't, you have to be able to see these numbers. So until you get familiar with those, go ahead and reference to that, but make sure you're practicing those so that it gets easier without the chart, because on the EOC and moving forward in other classes, you're not going to have that chart. All right, so I've got the square root of 15 over the square root of 64. All right, square root of 15 is just going to stay square root of 15, and square root of 64 is going to become 8. 8 times 8, again, is 64, so it's a perfect square. All right, B part says the square root of 81. Again, you can look at the reference chart if you need to. You can see that 81 on here is going to be 9 times 9. So it is a perfect square. So I'm going to have the square root of 81 over the square root of x squared. Both of those are perfect squares, so that's going to become 9 over x. And that's how you simplify using the product and the quotient property. All right, we've got a study tip here. It says, in this course, whenever a variable appears in the radicand, assume that it is only non-negative values. All right, so basically if it's under the radical sign, just assume it's non-negative. Assume it's always positive, or there's a few extra rules that you have to apply, but you'll learn those in classes beyond here.